All right, welcome to my webinar on preload measurement circuits or circuit for bolt clamped ultrasonic Langevin transducers. My name is Hussein Shakani. I'm representing my company, Ultrasonic Advisors. We're going to be talking about a couple of topics regarding measuring preload. It's often an elusive, confusing idea. There's a lot of different information, different ways of going about it. I'm here to show you all a really simple way, a straightforward way, provide a calculator, provide a demonstration, and answer your questions. And there's a lot of things to say about preload, but this is like if you're going to watch one presentation on preloads, which I don't think there's any online available right now. But if you're going to watch one, you want to attend this one and you want to listen to this one afterwards too. So I will show you how to make measurements like a pro. Assuming that I'm a pro and you're going to be doing what I'm doing, then you will make it like a pro. So I'm going to talk about the role of preload in ultrasonic bolt clamp transducers, the theory of calculating the voltage. Also, I'll have a video of a demonstration of me torquing and fastening and loosening a bolt, measuring the preload voltage and showing how that relates to megapascals or force of preload. And just a bunch of different things about the experiment, but most importantly, I'll be showing an extremely simple circuit, a reliable, easy way to measure the preload voltage, which is going to relate to the preload force or pressure, if you consider area. And this is the basic structure of a bolt clamp Langevin transducer. There's a horn, there's a back mass, there's piezo rings, electrodes, and there's the bolt that puts everything together. And as you can kind of see here in this image on the right, we have tension in the bolt, and we will have compression on the crystals. This is an absolute scale, so everything is just blue is 0 and red is the highest, but there's compression on the crystals and there's tension in the bolt itself. And you can see kind of here, there's like stress concentration areas near the edge of the crystal stack here. So there's different things to consider. We won't talk about that today, but we're going to talk about how to ensure that, how to know how much force you're putting on, and why do you even care about how much you're putting on? Like, what's the purpose? And I'm going to get to a video demonstration. I'm going to start off with a bang. The kind we all like, not the kind we don't like. But I'll talk about just quickly introduce my company because this is partially marketing and partially just plain fun for me to explain these things that aren't of this information that's not easily available. So my company was founded in 2019, and I support companies developing all ultrasonic transducers of many different types. Many of them have been bolt clamped Langevin transducers that I'm showing today, but they've also been of many other types like bending, sensors, ultrasonic motors, different medical applications. Usually I don't do things in imaging, but besides imaging, most applications are relevant for my expertise, extremely relevant. And I support companies through simulations, prototyping, hardware like circuits, and just all the areas that companies have trouble with or maybe lacking expertise. I can provide fill those gaps so you can even make better use of your in-house staff for what their knowledge base is. So if you want to schedule a consulting call with me, go over to my website, ultrasonicadvisors.com, and you'll find your way to book a call for consulting work. But let's go ahead and share the video of preloading and loading. And after the video, you're welcome to jump off the webinar, but because a lot of the value is here, and I want to make sure that we start off with that. And then I want to optimize for video clip. Share, no, don't share sound. Okay, share. All right, so do you guys see a video player? I think you should. Right now. Yep, I think I'm sharing that. So I will start, and I'll just make sure this is on faster speed so you guys don't get too bored. But this is the piezo transducer inside of a collet. And here I take the wrench and I untighten it, and untightening it creates a voltage on the multimeter that you see here in the corner. And the only extra part in the circuit that I've added is a 100 microfarad film capacitor. This is the most essential basic way of measuring preload. You hook up a 100 microfarad film capacitor, and that does a lot of things for you, but it helps us to then measure the preload voltage. So I undo it, and it's going to be pulling it. Okay, now it gets to be negative 18.6, and then of course it all falls apart because I don't have the right attachments, but it still works. So negative 18.6 is the voltage that was generated due to the piezo stack uncompressing on this 100 microfarad full capacitor. Well, that's going to be 0.0. You can multiply that voltage by the capacitance to get the charge. And that relates to voltage. And I'll have all these calculations for you, and I'll show you where you can have that. I actually created a calculator on my website. So I retorque it now. This is retorquing it. I'm torquing it back to 0 volts, so what it was originally. So normally you wouldn't torque it back to 0. You would just torque it to your value. And if you hooked up your leads properly, you'll get a positive voltage if you were doing it going forward, like assembling the transducer fresh. But I left that voltage on there. See, you saw that I torqued it, and it went back to 0. Like volts, because I just pretty much put the charge back on by compressing it. And it's important to measure the use a torque wrench just to ensure that something didn't go wrong in the bolts tightening process. So you use a torque wrench that you can measure the torque. The torque measurement device. So this is at 1.83 Newton meters. So that's cool. And then let's see and I have images of these at the end, but I just wanted to show you the demonstration because I feel like it's just more engaging if you just have something to actually see and get, know what the heck we're talking about. So if you're new to this area, you're like, so why are we doing this? So this is assembling it. This is to know how much bolt. So I undid it, and then I got negative 18 millivolts here. You can see. And I'll have images that will actually just share the key points here at the end. And then here this is important. I short the leads. That zeros the scale. So then I can now, let's say if you're in a manufacturing environment, you may have a button, or you may ask the technician to shorten the leads, and then you're ready to measure the preload for your next device or your next transducer that you're going to assemble. Then right now I'm going to be taking apart the transducer. And I'm just going to show you the components. This is an ultrasonic scaler, so it has 2 crystals. It has a horn, and it's something you can easily purchase from like an online store. Like you purchase an ultrasonic scaler consumer, you can easily get this transducer. And the parts for the collet for fixing it and everything is kind of inexpensive and accessible, and that's one of the reasons I showed it here today. So there's 2 crystals, there's 2 electrodes, and there's a horn, and I'm going to be laying it all out right now. Let me know if you have questions as we go. But we're going to be doing a couple of. So that's the horn. I'm going to be it's going to be laid out at the end. Let me just fast forward here. There it is. So that's everything. The horn, and I'll be okay. Let's go ahead and share my presentation once again. And we don't need to optimize for video. Okay, how about that? Hopefully, so somebody asked, does it need to be a film capacitor? Yes, absolutely it does. Because the voltage the charge will just drain in the capacitor. Normally this is not a problem for most applications like microamp or like picoamp. Like drainage is not a problem, but it is a huge problem here. If that's so like the ceramic capacitors or like a special electrolytic, they're obviously polarized, most of them. So that's going to be a problem there. So why do we preload? And I'll explain more about that in a few minutes. But I'm trying to keep it basic at the same time. So why do we preload? There's 2 reasons we preload, or basically we tighten the bolt to compress the crystals to hold everything together. One is to hold the crystals in compression, because it keeps them from going into tension. And tension is bad for piezo ceramics because they'll fracture more easily. So if you lower the baseline, the DC kind of baseline static stress, you're able to actually excite them with larger AC excitation. So it keeps them from fracturing and also out of the nonlinear region, which will reduce their quality factor, cause the properties to become unstable, and pretty much make a poor transducer performance. And secondly, it keeps the structure together. But like, wait, we could just use glue and just glue everything together. Why do we always use this bolt? Well, the bolt is used to keep the crystals in compression. That's one. The epoxy will not keep them in compression to the extent that you need them for power ultrasonic transducers. This is why all power ultrasonic transducers have preload, because you will not be able to excite them with enough amplitude if you do not apply a compressive preload. That's kind of like the bottom line. You need power, a lot of it, or a good amount, or a decent amount. You'll need to compress them. Easiest to do with the bolt clamp transducer or similar topologies, which there aren't many others that will do the same thing. The other thing is that keeps the structure together, so we can't use epoxy because it doesn't apply compressive force. But keeping the structure together does not only mean like physically keep them in contact, it keeps them in intimate contact, which is very important for acoustic energy transfer. Because if you don't have enough preload, you may have enough preload for the excitation you need, but you don't have like to combat the alternating stress from resonance, but you don't have enough to because the surfaces when they contact, they're not perfectly flat and just like touching like flat like this. They don't touch like this, like completely like 100%. There's surface roughness, surface texture, so that pressure makes them into better intimate contact, allows those surfaces to kind of mate, flatten them out against each other, and increases the quality factor due to that purpose. And then hence it reduces the impedance at resonance. So how do we measure preload? So preload is important because it keeps the crystals together, keeps the structure together, intimate contact, and crystals in compression. So we need to measure how much we put on because that's a sensitive amount. And I'll describe why we need to calculate it and how do we calculate it. But I'll mention here 2 ways to determine the preload. And there may be like a hybrid. There's some hybrid methods you could say, but I won't speak about that. So the method 1 is you can use tables relating the applied torque on the wrench. Like I had the wrench, I got 1.83 Newton meters. You can relate the applied torque to the preload force. There are tables for this, like M5 screw, you apply this many Newton meters, you're going to get this many newtons of preload force. Okay. Those are tables, and it'll describe a friction coefficient. And that's the problem there, that friction coefficient, because the surface properties of the bolt threads are not very, very finely controlled. And even so, probably if you had there would be even small imperfections could cause huge variations. So the results can vary plus or minus 50% for torque to preload force, but that's the worst case. But it can be highly variable. Like some cases it could be very consistent, then you'll have an outlier. And well, that's one product that's not going to work for long term. So that can be very problematic. Oftentimes, and many of you who do have ultrasonic transducer assembly or manufacturing experience or R&D experience, you'll know that even if you assemble everything as much as you can the same, the results will have a good amount of variability, and that confuses some people. So because the end product will have a bit of variability, we need to make sure everything as much as possible that goes into the transducer is similar, because we don't have that signal to noise ratio at the end of the process to know all the time what's a good and bad transducer. But we really rely on assembly processes to ensure quality, because you can't always measure those properties at the end. So the method 2, which is the one I'm going to speak about, and I put in bold here and I highlight it, then I'm going to unhighlight it because that's really hard to read if you highlight it. It's kind of annoying. So method 2 is you use the piezo crystals themselves as a self-measurement transducer to determine the preload. What's a piezoelectric material? You apply a force and you get a charge. So why don't you use that charge developed on the crystals to measure the force, because they're a force transducer. In other applications, they're literally used for accelerometer, like measuring measuring acceleration, or in other cases measuring force. So why don't you just use them here, because they're already there? Perfect. But so piezo properties can vary. You specify a specific type of material from a manufacturer, and they're going to vary over time. So don't give them too hard of a time for having them vary. But sometimes they vary too much. That's an issue. But we can measure the properties beforehand of these crystals to improve the accuracy. It's not necessarily possible with method one, because whenever you torque you could torque the bolt, and I could get into this, but like you change the friction coefficients once you torque it, and it's just too many like mechanical steps. So the piezo crystal is like inline live measurements of the exact thing you're trying to measure, so it's kind of more direct. So this is the method that in almost all cases that companies are using the crystals. I've in rare cases I've encountered people using torque, but it can be used to decent like okay variability, but for high power transducers, it's not going to work very well. So method two, using the piezo crystals as a self-measurement transducer, and I use torque. Like why was I measuring torque then? I used torque to verify that the torque wasn't too high, because if the torque was too high, that would mean there's something wrong with the mating. So there's like some type of like cross threading or some type of burr, which is going to really affect the acoustic performance. It doesn't necessarily affect the immediate preload, but it's going to affect the long-term performance, which is why we do want a relative stability of torque, but we're really aiming for the crystal preload value from that voltage that I'll talk about. So we have to determine the preload stress. This is like an annoying topic for me sometimes, and it's a difficult topic for me to give consulting advice on. And what you don't want to hear from a consultant usually is like, it depends, right? Like, well, what do you like? It depends on a lot of things. So it's hard for me to answer the question exactly, but I can tell you the means and methods that you can come to sort of understand where you need to be. So there's several options, and they all make a lot of sense, because ultrasonic devices have their assembly has a bit of their own. It requires some experimental kind of back and forth. You can't just FEA your way through it and expect it to work the first time. You can't just calculate all the time your power requirements, but you start from a known place. I love to start from known transducer designs usually, instead of creating something from scratch or something new, because every design that you make is going to have its own peculiarities that you're going to have to solve. Like one has a bolt resonance that shouldn't have been there, but it is. And one has a bending resonance that shouldn't have been there, but it's there. And another one has a preload stress concentration issue. It shouldn't have been there from the FEA, but it is. And one has a electrode resonance. Like like the electrodes are moving around and resonating, like shouldn't have been there, but it is. So you need to use FEA and other calculation methods to get your first prototype as fast as possible. So method one, use FEA to determine the prestress needed to keep the crystals in compression based off of the stress profile generated due to resonance excitation at the appropriate amplitude. I have a partial webinar on this. The first webinar I did, webinar number one, using modal analysis and Fusion 360, which is a CAD and simulation software to do. So you can use FEA to determine based off of that what's your need based off of the resonance. And this is not talking about the intimate contact between parts. And then option number two is another simple one, like determine the charge generated from the target ultrasonic current, and then you can determine the preload based off of that. Because like if you think about it, when the crystals are oscillating in resonance, they are that charge, that current is caused from charge. The charge is coming from alternating displacement or a stress. So the static preload has to counteract all of that excitation to keep it into compression. So these two are mostly talking about putting it into compression, holding it there. It's not specifically addressing the intimate contact, which is purely an experimental thing you need to work through. So these kind of tell you, well, what's the best case scenario for the stress I'm putting on. And as you obviously get lower in stress, you will be those surfaces will kind of start to separate more and more as you get to a tension state. And remember that the whole crystal, there's a stress distribution. The inner diameter has more stress than the outer one. So if you applied 1,000 newtons of preload or 10,000 newtons of preload, it's not shared equally. So you have to preload according to the maximum stress seen according to the distribution. So sometimes the distributions are matched from decently well from resonance to static preload, but sometimes they're not matched very well. So you may have to overcompensate your preload because your AC resonance has a different stress distribution. But in general, okay, start with a 40 megapascal starting point. That's like the symbol, like because that's known to help. And there's different things in literature, but it all depends. You start from somewhere and you have to experiment, iterate, calculate, do it all over again, add safety factors. Usually FEA is the worst case scenario for static preload because it doesn't account for surfaces like permanently deforming as the surfaces come together, especially if you use soft electrodes in between those critical surfaces. It won't account for that absorption of that high stress. So here's something that probably deserves its own slide. Let's just duplicate this. This is why I use this view instead of the other one, because I often have to change things. So you have too much preload, you could crack or depolarize the crystals or fatigue the bolt. Although crystals are piezo crystals are ceramics, the PZT. So PZT ceramics are actually scientifically not crystals. They are ceramics because they have multiple grains. But we call them crystals because their first piezo materials used were crystals. That name just stuck. So if you provide too much preload, you'll crack or depolarize the crystals, and you can also fatigue the bolts or cause it to yield. Fatigue, basically cause too much yielding. A little bit of yielding is actually okay, possible, especially at the threads. You have to experiment to find out. And some of these things won't reveal themselves initially, but they will reveal themselves after significant amount of testing. So it may look fine initially, but you realize that based on preload levels, there are some there are some transducers that will fail earlier than others based on longer life testing. So that's also important to consider. Once you have your R&D work kind of running smoothly, then kind of run a bit of a harsher test that might simulate its length of work. And this is why a lot of transducers have this burn-in period where they are tested, maybe even continuously for 24 hours to weed out transducers that didn't work so well. And that's just the name of the game. You got to do the testing and some will fall out and you'll always have some hit on the yield, but God forbid it happens to the customer. We don't want that. So too little preload, performance suffers, so max power reduces, impedance increases, quality factor decreases, frequency is variable, often lower, and nonlinearity occurs. If not, the thing just breaks because the crystals start to slip and crack because of that issue. So you have to figure out what the right value is, and 40 megapascals is a good starting point. So here's the circuit. What the whole presentation was about. What the circuit is a transducer, and you use a microfarad film, a range film capacitor. I mean range, not that it's variable. The range means that like it should be several microfarads. Multiple levels are permissible, but I'll give my advice right now too. And then you just attach your multimeter to it. It doesn't get more simple than that. I had other methods that I was considering showing because they're like a little more compact. I will tell you in probably the next webinar why I didn't, why I didn't choose a different method. I could put in one more component to actually further improve or make this more compact, but because film capacitors, especially large ones, tend to be large, they're not small. So, but anyways, you just hook up this in parallel and you hook the terminals to your multimeter. And that's kind of the circuit. It's not much of a circuit. It's more like just attaching something in between. Some might call it a circuit. I do, I guess. And I'll explain a little bit more. So if you apply a preload or a load to the transducer generates a charge. And this font here is Algerian. So the reason I use an Algerian font of 41 size versus a Calibri, I think, font in the body format of 26 size, and I highlighted it in yellow, this one. The reason I did all of that is because people think that transducers generate voltage when you apply a force. They don't generate a voltage. In fact, applying a force doesn't actually generate anything. It's actually strain. So we get stuck in this idea that force generates charge, and that's only in certain circumstances where the force is allowed to use strain. How do you have stress without strain? Well, you squeeze your transducer like this and you squeeze it like that, like hydrostatic pressure, but you apply enough force on the sides of your side of your crystal to keep it from displacing axially, then you actually won't generate any charge because you need strain in the thickness to generate charge. So it's actually strain, not really load. So I'm just letting you. So the boundary conditions matter. Your apparent stress to load ratio will differ slightly based off of your boundary conditions. But that's for me to care about as a consultant. You just need to hire me and listen to me. Maybe that's what we're all here for. Okay. Anyways, so applying a preload generates charge. It doesn't generate voltage. The charge is equal. Then I can zoom in here. That's the nice thing about that. Okay, the charge. I'm looking at this line right here. Let me do that. The charge is equal to the D33 multiplied by the preload force multiplied by the number of crystals. You increase by the number of crystals. Crystals are in series, so the charge will all accumulate. The D33 can be taken from a crystal data sheet. It's not so accurate, but it's a great start. It's a good reference. The charge is then stored. If you have this microfilm farad capacitor, the charge is then stored in the capacitor. And because the capacitor is so large, it's in the microfarad range. Usually the transducer is in the nanofarad range, low nano, like 5 nanofarads, 1 nanofarad, 6 nanofarads. If you use a 1 microfarad film capacitor even, you've dominated the capacitance. So if you measure a voltage, it will be this charge. It will be the charge that came from your transducer. The voltage will be a lot lower because its capacitance is a lot higher. But you will be generating that whatever voltage you measure, you can directly correlate that to the charge because you know the capacitance. And now there's a lot of reasons for using the capacitor, and I'll explain that in the next slide. There's like 5 benefits. I wrote 5 benefits and I can only come up with 4, so I added an extra one. And maybe I just repeated it, but I'll show you in the next slide. So thus, the preload force equals the capacitance that you added, the microfarad film capacitor, multiplied by the voltage, divided by the D3 times the number of crystals. And as we know, stress equals force divided by area. Usually represent that, and I'm gonna show you a demonstration, and I'm gonna provide you a calculator because sometimes we are not prepared to hear equations. Very rarely do we ever talk about equations. It's kind of interesting if you get out of college, like equations kind of go out the window a lot of times, except very basic ones. So why do we use this film capacitor? What does this do for us? It does 5 things. Number 1, it lowers the voltage. Lower voltages are easier to measure. You don't want to measure kilovolts or hundreds of volts. You want to measure volts or millivolts. It's easier to measure, and there's no chance for high voltage damage. Perfect. The other thing it does here is it establishes a known relationship between voltage and charge. You measure voltage, you know the charge because you know the capacitance. So it's very easy to calculate the preload because the only unknown here, technically in this equation, is the voltage. And once you measure that, you get the force. Nice. The next is that there's linearity in the measurement of charge. So the piezo crystal force versus voltage alone. So if you only have the crystal, this is only the crystal without the microfarad capacitor, that is nonlinear because the permittivity of the crystal, I'll write, extal. The permittivity of the crystal changes with preload force. So that means the capacitance permittivity, permittivity, so because the capacitance of the crystal changes, if you did preload only the crystal and you had a kind of advanced circuit to make sure that you did not that you were able to keep that voltage or charge on the transducer, then you will oh yeah, somebody asked a question, but yeah, so if you do that, then you will actually not being you don't know exactly what you're measuring. So you still got to go ahead and probably have a circuit to measure charge. They do that in polarization electric field tests by putting a capacitor in series. That's something you could do, but why would you do that? I guess in this case. So somebody mentioned, does D3 vary with geometry or was just determined with material? Yeah, so D3 is determined by material, but there's also a lot of processing conditions that can change that. And they're, PZT materials are doping based, and they are thermally sensitive, and they're very sensitive to processing conditions. So there is variation in the material, so that needs to be accounted for when you design products. Yeah, so and what ways can you account for that? Well, I think either finding a previous webinar of mine where I might talk about it, or maybe hiring a consultant could help. I don't know, or just figuring it out because we're engineers and we like to figure things out. So as do I. So there's linearity. It also keeps the crystals under short circuit conditions. This is an interesting one. The crystal voltage is not allowed to change very much during the compression part, right? Because the capacitor takes the charge and then the voltage is actually very small, so it's effectively actually under short circuit conditions. And then that makes the crystal compliance of constant electric field be almost exactly identical to that. So the crystals can displace more with your torque wrench. That makes it slightly easier to apply the torque needed and the preload needed. And I believe also if you short the ceramics after you apply a torque in open circuit, you probably will lose some of the preload because the ceramics will become some of that energy will go into creating the load. So there's probably a diagram I could show, force displacement diagram, if you load it, and I think I drew it, but I decided not to share it. But yeah, it keeps the crystals under short circuit conditions, and the crystals are a little bit more compliant, so that you can squeeze them more, which is perfect because that's how they're going to be operating. It increases the time constant during measurement. So you have this capacitor here, and if you're measuring voltage with a very common device, which is a multimeter, it has a 10 mega ohm impedance. So whatever load you connect to it, it has 10 mega ohms, and that capacitor will leak through this 10 mega ohm resistor. So if you're just measuring the transducer itself with a load, you would definitely not be able to measure this with a with a normal multimeter. Because if you had, let's say, 1 nanofarad and 10 mega ohms, the charge would just run out instantly, and you would not be able to measure much of anything. So having a microfarad film capacitor that high level also makes the voltage measurement more stable, and you can also measure it then with an ordinary device. Oh, if only there was a prestress calculator, one might pray and ask. So I am here to answer that prayer of yours. So prestress calculator, I added recently, this maybe as of yesterday or the day before, a resources section on my website, which is ultrasonicadvisors.com. And there's a resources page. On that resources page, the only thing I have right now is the preload to voltage calculator, and that takes you here to this calculator. You can also use it in reverse by putting desired pre-stress values, but you basically enter in the desired pre-stress. Let me zoom in here. You enter in the pre-stress, the outer diameter, the inner diameter of your rings. These are all ring based. And yeah, if you don't have a ring or something like that and you want to do some calculation, just make sure the area matches up because that's calculated. It's not too hard. Then you type in your D33. You can use the assumed value from your manufacturer, the number of crystals you have, which will be 2 or 4 probably for a power transducer, the parallel capacitor you're using. Then all of these things will be calculated for you, but the thing you want is here, 91.36 millivolts that you need to shoot for. Now, what if you wanted to calculate the megapascals per millivolt? Then you could put in, I guess, 1 megapascal, and then you'd get the amount of millivolts that 1 megapascal is. You guess you could just invert that. I just need to add that. I think I had it here, but I just forgot to select that cell. I'm going to be using this live, so this is not everything here is going to be demonstrated and made easy peasy for you. It's a thing we say in America. I think there's some international people, European, I think here. Easy peasy. Use that one next time with your American colleagues and watch them be confused as to why you're talking to them like a kid. Anyways, I have a couple of children. Yeah, I like to make things easy peasy for them and you too. So choosing a capacitor. We had this question. And if any other questions, please ask. I don't like to keep talking to myself. So please ask a question and I will answer it. I like asking questions personally during things like this because it helps me stay engaged and or else I kind of just am sitting around. And that's why it's great to attend live so you can ask a question, you can stay engaged, and you can kind of have that on your schedule. So choose a capacitor, microfarad capacitor with low ESR. They're usually pretty large in comparison to other capacitor types. Do not use a film capacitor. Do not use an electrolytic capacitor. And I'm actually going to give you a specific recommendation in the next slide. If you're using a normal multimeter to measure voltage, it will leak out voltage according to the RC time constant. RC time constant is this: your microfarad film capacitor and your parallel and your resistance of your measurement source, which is going to be 10 mega ohms. If you're using a normal multimeter, it will leak voltage. So the time constant decay is the resistance times the capacitance. That's to get to 30%. That time will get you to 30% of your original voltage value. If you had measured 100 millivolts, the time constant, I think it's about how long it's going to take to get to 30. And then it's it's exponential decay there. So if you had a 10 mega ohm impedance of your resistance of your multimeter and a 10 microfarad, that'd be 100 seconds. But if you had a 10 mega ohm and 100 microfarad, that would be 1,000 seconds. And just to give it to on kind of practical terms, like this is the plot here. Let me just get this to be normal size, 100%, please. So over 20 seconds, the 100 microsecond case will go to 82%, and the 1,000 microsecond case sorry, 1,000 time second time constant will get to 98%. So practically, this is what it means. 100 microfarad will lose 1% of the voltage over 10 seconds. Preloading actually takes about 5 seconds. So that is like you are not trying to get preload closer than 1%. There's already so much error in the D33 and how much and loss of preload, and 1% is you don't care about 1%. That's not a problem. That's like kind of splitting hairs, more than splitting hairs, like splitting bacteria cells or something even more, splitting microns even. Like it's not important. However, 10 microfarads will lose 9% over 10 seconds. I don't like that. That's a lot. That's uncomfortable to see your measurement device losing voltage that quickly. But I highly recommend the 100 microfarad case. It has one drawback in that now all the preload values will be in the millivolts. Like it can be as low as 10 millivolts depending on your device. The device I showed was actually, what was it, 18 or 16 or something like that millivolts. But let's talk a little bit more about that. So I recommend to use a 100 microfarad motor run. This is like the name of it. If you search for it, you'll come up with the type that I'm talking about. Motor run film capacitor. Multimeters have a resolution to 3 digits, which is plenty. So if you have 23.8 millivolts, that is plenty to measure that. Also, the large capacitance will stabilize in millivolt range. So you may feel like it's a small voltage, and normally maybe even your millivolt kind of like jumps up and down. First of all, use shorter leads and everything, but this large capacitance will stabilize your voltage. So that's great. It's like a filter in itself. So you have a lot of other options to measure the preload voltage. You can use an electrometer, which is a device which costs several $1,000s. It's a very high input impedance, tera ohms. That has worked very effectively for clients I've served in the past. Use high input impedance op amp buffer. No, I haven't seen anybody do this exactly. I've seen them use it as a charge, what is it called? Integrator charge amplifier sometimes. But you have to be very careful with this because it also has a bias current which can drift the output. So it takes some design, I guess, and a lot of consideration. And I haven't seen a client. I've seen people have it but not develop it per se. So I might do it soon, but we'll see. And you can also modify a multimeter to exhibit very high input impedance, hundreds of mega ohms. And I think this is going to be the topic of my webinar next week. I'm going to start weekly webinars in order to address the many topics that I want to talk about on Preload, but simply don't have the time for. And I'm running out of time here. I'm talking a lot. Sorry about that. But I'll try to be quick now because I told you already a lot. So how do you find the capacitor? You search in Google motor run film capacitor 100 microfarads, and you buy the one that shows up. That's that simple. How do you know if you have a good capacitor? You charge it up with a voltage source and you hook it up to multimeter and you just watch it. You just sit like this and you just watch it, and you can calculate the time constant based off of the voltage decay. And if it's like, if you have 600 millivolts, it'll be like, you'll see the voltage drop down. But you have to remember, if you have 600 millivolts, 0.6 millivolts is 1%. So that should take you about 10 seconds. And that's, you're not there to preload the capacitor and just like sit there and like watch it. Like that's not what you're there to load it, find the maximum value, move on. The maximum error you're going to probably have is 1% of that value. So it's extremely practical to use this method. Here I'll just show you pictures of what I showed you in the video earlier. Here's the ultrasonic scalar transducer. Here it is mounted in the device. I'm using this torque wrench to measure, have a torque meter, measure the torque. Here's the capacitor, the multimeter, and it connected to the leads of the transducer here in the device, or the collet, I guess. Everything's ready to go. 0 volts there. all done, negative 18.6. If you had actually hooked it up positive and negative and you started from 0 and you torqued it, you would get 18.6 positive, which is basically what happens. So I have the torque was negative 2.05 Newton meters. You've seen all this before. I refasten it back to 0 volts. Basically, I'm adding 18.6 millivolts. Well, there's probably some voltage decay, and that's we're not, this is just demonstration. If I was clamping it up to 18.6 volts, and it happened very quickly, as you saw. It happened, I probably torqued it within 3 or 4 seconds. So the retorquing was 1.83 Newton meters. I loosened again, and I disconnected the terminals, and notice the voltage remains on the capacitor. So it's not dependent on you staying at the transducer. The voltage is now on the capacitor. If you short the leads, you zero out the capacitor for your next run. If you're doing an assembly, you would want to do that, or you have like a button that shorts the leads. And then I'm just going back to the chat here. Somebody mentioned that the resistance source from the ESR and the meter should be negligible. So the meter has a fixed value. You can even measure the 10 mega ohm resistance from one multimeter to another. What multimeters can measure mega ohm resistance. So if you set a multimeter to the millivolt range and you plug in from another multimeter to measure resistance, you'll get 10 mega ohms or 11 mega ohms. So the capacitors themselves are extremely low. So that's the case there. In terms of the type I specified. So here's the transducer disassembled, and here's the calculator. I typed in I did it backwards. So I knew I had 18.6 volts, 0.7, and I typed in the outer diameter, the inner diameter. I assumed the D33 value at 2 crystals. I knew my capacitor value, and then the 18.6 was calculated, and I kept changing the preload value to get to the approximate preload that I found, and that was 56 megapascals. But that does depend on what was the D33 of the value of the crystals. So you can look at your manufacturer data sheet. I'll explain in another webinar how to calculate that more accurately, but this will at least help you keep consistent in terms of how much you're preloading. It'll get you leagues beyond what it was just with torque, measurement of torque. So I realize I have a lot to say about this topic, which just kind of shows I actually aimed to make this webinar short, but it didn't end up being short. So I'm planning to continually do videos on, or short webinars on this topic, all the way from D33 measurements to various ways of preload measurement with voltage, crystal voltage, and crystal current, even current. I'll show you in a couple weeks. Crystal stack position, like FEA stuff, experimental optimization, which I might move it around, transducer design to improve uniformity. The topics will change in order. I guess it'll kind of go off what seems easiest and most relevant for me, natural. Right now, I really want to talk to you guys next time about using a normal multimeter and making that into a high impedance device. Instead of having it 10 mega ohms, have it be hundreds of mega ohms. There's a method to do that without sacrificing voltage resolution. I want to share that with you next time. So with that, I will ask for any questions, and I will stop this